Hello again, class, and welcome to week 5. I decided to actually do a presentation about F distribution, which is an important concept prior to ANOVA or analysis of variance. So I'm going to attempt to uh, explain what an F distribution is all about so you will have a better appreciation of what ANOVA or how ANOVA functions. So some basic concepts on F distribution. Um, when we are looking at F distribution, what we're trying to explain is that we are trying to compare the variances of two populations using the F ratio and then um, standardizing that distribution and using the F ratio value and then calling it an F distribution. Now, as I mentioned in the on the other slide, on the other presentation, is that the F ratio is an important concept to remember in ANOVA because as you look at ANOVA's conceptual framework, ANOVA utilizes the F ratio, which is the variances of the two population when it's trying to determine statistical significance in the means between the two populations within and among, and then also um, across the three uh, different populations, the three different population mean. So F ratio is a fundamental part of the very complex mathematical formula for ANOVA. And as I mentioned earlier, F ratio is simply a ratio of the two variances from two samples. It is a component, a very important component of ANOVA. And the F distribution or F statistics is an inference procedure that deals with the equality of the variances of two normal population. So this is a new concept that I'm introducing, is that the equality of the variances of two normal population. Again, we have to remember that variance is part of the measures for dispersion on how big is the variance. That is what the F statistics is trying to determine. It is a test for the equality of the equality of the variances of two normal population. Normal means it has a normal distribution. Continuing on with the basic concepts of F distribution, this F statistics was named in honor of Sir R.A. Fisher. He's a very famous British statistician, and we also have the Fisher exact test in his honor. And the history of the F statistics was that at one time, statisticians actually recommended performing an F test for the equality of the variances of the two normal populations before going on to the t-test statistics. Well, that is no longer thought to be useful in our current times. What statisticians found in that is that in small samples, the F-test can't reliably detect quite large differences in the variance because that's Again, the law of the larger sample. So if you have a small sample, the f-test cannot reliably detect the quite large differences in variance. Now, in the opposite side of that, or the opposite argument, is that in large samples, the f-test will reject the hypothesis of equality of variances for differences that are completely unimportant, because that's the function of the large sample. So currently, the only time we utilize the f-test is when there is a case where the researcher and the statistician genuinely um, interested in knowing whether the two variances are equal, such as when you perform your ANOVA analysis, because the equality of a variance, the equality of variances of two samples is an assumption that cannot be violated in ANOVA. Additional basic concepts that's related to F distribution is that the curves in F distribution, just like what we talked in, we have our Z curve, we have our T distribution curve, and just like those two statistics, the Z scores and your T test, the F statistics also has a curve, but this time it differ not only according to the size of the sample, but also on how many samples are being compared. So because the F statistics utilizes two ratios, you're also going to have the appearance of two curves for F distribution. So basically what you would expect when you look at an F distribution is that the F distribution has two sets of degrees of freedom. The first degree of freedom is the degrees of freedom for the numerator. And then the second degree of freedom, expressed as df2, would be the degrees of freedom for the denominator. The designation of an F distribution with 10 degrees of freedom for the numerator and 15 degrees of freedom for the denominator is expressed as df equals df1 comma df2, and that would be a df of 10 comma 15, close and open parentheses. So an example of two F distributions, one with a degree of freedom 8 and 40, and the other with a degree of freedom 8 and 4, is illustrated here on the graph in the middle of the slide. So the top F curve, you have the degree of freedom with 8 and 40. So again, remember that the first one, the degree of freedom for the numerator. And then the second degree of freedom is the degrees of freedom for the denominator. So here, the notation is that in the expression of degree of freedom, I and j, the index I is the degree of freedom of the numerator, and the j is the degree of freedom for the denominator. As you notice here in this 2F distribution, both F distribution curves are right skewed. But one of the things that you should remember when you look at F statistics is that the larger the sample it becomes, the more the distribution or the curve's gonna look like normally distributed. It's gonna almost follow your normal bell curve appearance. So sample size has a major impact on the appearance of the F distribution curve. So the F distribution is skewed to the right. The extent of skewness depends on the degrees of freedom. And as skewness and degree of freedom increase, the distribution becomes more symmetric. So when do you expect the distribution to become more symmetric? Well, we know that uh, measures of central tendency and dispersion tells you that the larger the sample, then we know that it will be more symmetric to the mean. Therefore, this is an expectation that as your skewness and as your sample increases, which means that your degree of freedom also increases, then the distribution becomes more symmetric and will follow the almost perfect appearance of a bell curve appearance. T-test is extremely sensitive to the assumption of normality, even in large sample. And that's why F-test is the test for homogeneity of the variance. So when you do your ANOVA, you don't be surprised if there's always going to be a test for homogeneity or test for heterogeneity. They're the same, but it refers to F-test. So a sample is said to have a homogeneous is said to be a homogeneous sample when the sample variance are effectively the same. The opposite, of course, is that it is heterogeneous if the sample variance are not the same. So F-test is the test for homogeneity or heterogeneity. It tests for the equality of the variance. And in some, I think in SPSS, they call it the Levene's test. In some software, they call it just the F-test, and you will see the value of the F-test. And you might also encounter in some of the publications, the statistical technical terms for this is that if the variance, if the variances are homogeneous, then they call it homoskedasticity. And if it's not, then the sample variance is described as heteroskedasticity. So this is an important component that every statistician will use when they run ANOVA, that there has to be equality of the variance. Now, what are you going to do then if your ANOVA shows that there's no equality of the sample variance? Well, you cannot do ANOVA because ANOVA is parametric. Then you're going to resort to the non-parametric equivalent of ANOVA, and that is the Kruskal-Wallis H test. That is the non-parametric test that will also examine the means of more than 3 population in a non-parametric and in cases where the equality of the variance is violated or there is heteroskedasticity in the data, then you have to do Kruskal-Wallis H statistics. So in summary, the F-test utilizes the ratios of the population variances, and this test statistics should be restricted to the case where there is a genuine scientific interest in whether the two variances are equal. So think of some of your research question where you really want to know that the variances of your sample are equal, then that's going to be the perfect test for that scientific inquiry. That would be the F-test. So this brings you to the slide that reminded you about ANOVA, that in ANOVA, it requires that the variances of the samples are not different, though some departures are accommodated, but to be strict, you need to do an F-test, or the homogeneity of the variance test, and in some software it's called the Levene's test, and you have to make sure that you do not reject the null hypothesis, that the value of the F-test is not the critical value, because you want your variance to be equal. So that's the null hypothesis. Therefore, when you look at ANOVA, you have to make sure that the t-test statistic value is not in the critical region or not significant, and you should not reject the null hypothesis of the f-test, which is the homogeneity of the variance. If your f-test is significant and you're going to reject the null hypothesis when you're running your ANOVA, then you need to consult a statistician, and I think you have to use the non-parametric equivalent of ANOVA, which is the Kroskal-Wallis H test. All right, so that summarizes the lecture on F distribution. If you have any question, let me know. Feel free to email me for short questions requiring short answers. If your question requires long answers, it's better to do FaceTime or perhaps Viber by phone. All right, until next time, we will be talking about correlation, Pearson and Spearman's, and also I think that that's going to be the last lecture we're going to cover for this entire course. And then we're also going to have just video lectures on the different practical applications of the different statistics that we have covered using SPSS. So I hope that my technology will allow me to open my SPSS, and then it will record the way how it records when I'm using PowerPoint. If that's not possible, then that means I have to take a screenshot for every single step on SPSS and then put it on a PowerPoint slide, which is a little bit tedious, but I can do it. All right, well, that's about it for this week, and I will catch up with you for correlations. And then we're going to do a lot of practical applications of your test statistics so that you will be ready for the individual final exam. Bye, class.